Hopefully you can see that. Is that right? You can see that? Not. I think remember one of these times we tried doing this, I had myself muted, so hopefully I don't do that again. So the way it's structured, just so you know, again, just to reiterate that, starting tomorrow at 2 p.m., I'm just going to post it on D2L, and then it'll be due 24 hours later. Okay, yeah, I'm going to break it into two or it's the same idea. We're going to have conceptual questions for a third, a problem that's going to be focused on beam design, and then a problem that's focused on column design. Okay, the short answer stuff, the conceptual questions at the beginning will be for the whole semester. Okay, but it still is going to concentrate on steel mostly. But anything from the beginning part of the semester is going to be fair game, at least conceptually. And then the other thing is that component of it, the conceptual questions, I'm going to put on D2L. It's going to be a quiz on D2L, similar to like the lab quiz you guys did. Okay, I think the idea, I don't know if I'm going to I'm going to set it up so that you could start it any time in that 24-hour period, and then I'll give you like an hour or something like that to work it out. But it shouldn't take you that long to do the little short answer, true, false. Did that work okay for you guys on the lab final? Maybe, maybe not. It worked. He graded all of them already. I don't hear any major complaints. No major complaints. All right. Okay. So I think it's going to be same idea for the conceptual, and then the other two parts will just be you just work out the two problems, and then I'll set up a box in Gradescope, and you'll submit it through Gradescope, similar to what we did, very very similar to what we did for the last exam, and then I'll go through and grade it. So, what else here? Let's see if I can see chat. Anyways.
So Mike, just one thing on the D2L quiz.
Yep.
I guess the only thing I would suggest is, if you have if it's like a multiple choice thing or whatever, just make sure that it's understood, like, are you supposed to check more than one, or is it one or something, just make sure the question is clear, you know what I mean?
Yeah, absolutely. So I'm assuming it wasn't clear last time. There's a couple problems.
No, there were a few of them where it was like, okay, I mean, I don't know. I don't know how many to pick, or if I'm supposed to pick one, or I mean, it seemed to all work out at the end, but it just wasn't totally sure.
So. Yep, sounds good. Yeah, Jaden did that one, and so I'll double check that I try to avoid those. I think he's going to put this one together for me, but then I'll make sure that it's all squared away. But thanks for the feedback there. Back to school, Paul. Now, so there's the kind of overview of how it's going to be structured and stuff like that. The components of it. I mean, this. I gave you some. There's a study guide for the other two exams if you want to take a look at those. But again, the focus this one's going to be primarily on steel. So I was just going to go through what we covered in steel. Okay, we start out with material characteristics. I might just flip over to what we did. I'm just going to go through the notes here. Okay, so we talked about the design philosophies, LRFD versus ASD. We're going to focus on LRFD. The pros and cons, okay, of steel design. I hate to admit it, but steel is pretty sick. It works pretty well. It's very predictable. It's actually a pretty nice material. So it's got a lot of pros. It's got some cons, right? It melts, it rusts, it's fatigue sensitive. Everything's buckles. And that's something you should be picking up on this, throughout all of these, except for tension members. Buckling was an issue, right? It was instability kind of controlled the capacity of a lot of things, okay? And then we talked about material characteristics. We looked at the stress strain response, what the modulus was, what, some other key components were in there. And then we talked about the different types of members, right? Spent a little bit of time on this table right here and went over the types of members there were, and then what they were used for, okay? What else do we have here? And then we got into tension members. And tension members typically are going to be part of something. You don't usually just have a tension member, just something that's carrying tension. It's usually part of a truss or another type of structure. We introduced this idea. This is the first place we saw this idea of limit states. Like, how is the member going to fail? It's either going to have yielding of the gross section, fracture of the net section, or block shear. I think it's worth looking to see what block shear looks like. Whether or not you need to, you don't need to study this too much on how to well, we didn't talk about how you calculate it, but just knowing what it looks like I think would be important. But there's this idea of this yielding of the net section versus the gross section versus fracture of the net section. So the way we did this is we calculated the capacity for each of these, and the lowest one controlled the design. Okay, and there were some and so that's what all this was. So just look back at the notes on how we go about calculating those capacities, right? And calculating this one's really easy, yielding of the gross section, but then calculating fracture of the net section is a little bit more complicated, right? Because you had to look at how many holes there were affected the capacity. If it was staggered or not staggered affected the capacity. If we transferred the load uniformly or if we transferred the load non-uniformly, you kind of get penalized if it's non-uniform like we have here. Okay, and so that's where these U factors play in, right? And it was pretty straightforward from there. I mean, lots kind of like little mini limit states within this limit state. Which hole is it going to rip through? Is it going to be, one hole, two holes, three holes, stuff like that? You had an assignment associated with that as well. Okay. The other thing I want to do, I want to take a quick second to show you, I don't know how many people actually watched those videos that Jaden posted. I'm going to show, it's a really cool lab. I just kind of want to show you what I wanted you to get out of it. And so I'm going to flip over to that really quick. I'm going to show you those videos. So the idea behind these, see if you could see this. Could you see this video? Do you see that? You do. Okay. So this is the one so you can see right here, there's 3 holes in it. These are the 3 holes lined up. Okay. Oh, I'm going to turn this volume. I think the volume's really high. Once you start loading this thing up, it's a long ass video. Right? It's 5 minutes long, so I don't know how many people actually watch the whole thing. We're gonna speed through it quite a bit, right? So this is a lot of it. We're just pulling. It's all in the elastic range right here, and then eventually you can see that right there is what's happening there. You can see it starting to yield around the holes. Right? You see how it's starting to flake off around the holes because it obviously is going to yield in that area right there because because that you have a reduced section there, so it's going to yield in that component first. But then what happens after that point? Before that yielding can spread, it rips through the 3 holes. So you can see it just yields around the holes, and then boom, rips clean through all of those, right? And then you calculated that capacity. That capacity is pretty dang close to what was predicted, right? So if you really dove into those numbers, it's pretty close to being what's predicted. It's just the FU is slightly different. Okay, if the second one that we did, where did that go? The second one we did, it has the staggered holes, right? And the same thing happens with this one. Is you go, at some point, it yields around the holes. Right? There it goes, it's yielding around the holes, but that yielding doesn't spread. And then eventually, it rips through the 3 holes right there. You can see it rip right through those 3 holes. And when you calculated those capacities, we looked at the limit state of ripping through 2 holes versus ripping through 3 holes, and it showed that it was going to rip through 3 holes. And it actually ripped through 3 holes. And it said it wasn't going to yield around the section either. This guy now, the last one we did, this is plate 3. If you actually look at the calculation, this one says that it's going to yield over the gross section, over the entire height first, and then it's going to fail through 2 holes, is what the prediction was. Ooh. Okay, and so here, if you watch it here, so there it goes, it starts yielding right around the holes again. But then once we keep loading it up, the least mechanism in this was yielding over the gross section. So we should see that yielding spread everywhere. And so if you keep going here, you see that yielding it's just taken off. Right? Now it's coming down from the top. And so look how much the thing is deflecting. You can see it just deflecting over this entire height. That is considered a failure mechanism right there. Look how much it's deformed. Like you can actually see it deform. That whole thing is yielded. Right? And so that is considered a failure mechanism right there. That would be the controlling mechanism. Eventually, though, once you keep applying the load, the whole thing goes through strain hardening, and then it rips through 2 of the holes. And what's really cool is that the calculation said it was going to do that, and then it actually did that. Unlike concrete, where we said it was going to do something and it didn't necessarily do what we said it was going to do, steel will do what it says it's going to do. And I think that one's pretty cool, especially this one, because you can see all that yielding before failure. You guys have any questions about that? I just wanted to highlight it because I think it's worth doing. I think that's some pretty good stuff. So then that's calculating the capacity of tension members, right? We looked at where in the code it talked about that. All this stuff is the code, the specifications. You know, the hardest thing about here is determining what this X bar was for calculating this U, but we had a couple of examples, and then you got to do that in your homework. Right, there's some stuff in the commentary as well, right? How to calculate what the L and the X bar are for the different capacities, and then we did an example, okay? So that's kind of steel thing. The one thing I wanted to point out that I did not cover before in class that you might want to look at, right, is that there are design aids for tension members as well. This is what I skipped over. It was like on a page that I didn't make it to. But this is table 5-1. This is under the tension tab. If you on your steel manual, there's a tension tab. If you flip it open, they have this, right? Axial strength in available strength and axial tension. Okay, and in there they just go through, right? And you look at phi PN, right, for a bunch of different members, right? A bunch of different members. And the way you work this is you look up the capacity, right? And then, I mean, so this is what the tensile load is. This is what your PU you would look up in here, and then you could design it according to these members over here. But the one thing is right, that you need to know what the hole patterns are and stuff, right? In order to use this table, you need to know what the A holes are, right? How many holes do you have in it? What's the U value that you're using? What's the net area that you're using? All sorts of stuff that it's very specific to the member. So to use this table, it makes an assumption that the effective area is 0.75 times AG, right? You don't know that that's going to happen because you have your own holes drilled in it or punched in it. And you have all the stagger factor that's floating around, and what are you using as a U value? All that's built into calculating this capacity. But to use this table just as a starting point to get going, they assume this AE is 0.75 AG, and then you could use this table. So I just wanted to point that out. That exists. And in previous years, I've looked up this homework problem, for instance, right, or this example problem, and you could use that table. But then you'd have to calculate what that effective net area is and whatnot. But anyways, I just wanted to point that out as we went through. Okay. Let's go to the study guide. The other thing I want to mention about the study guide here is I have gone through, in case you wanted to do this, in case you haven't done so already, I've called out where you might want to put tabs. Like where in the steel manual do you find these things, okay? So, table 2-4, you're going to talk about the types of members and the standard material it's made out of. Tension members, chapter D commentary, the tension tab, that's where you're going to maybe want to put your tabs on your steel manual, and then just to find the stuff when you go to do design in general, okay? And the same thing when you go down to flexural members, I've called out where the key components where you calculate that, or where you get the information from flexural members as well. Okay, that's something I've done over the years because I think I was trying to be consistent when I was doing notes, but I don't know if I was super consistent when I was doing that. So I might have missed I might have missed calling out certain sections of the code. Okay, the next thing we covered was flexural members. Okay, I'm just going to do the same thing. I'm going to go over to flexural members, look at our notes. Any questions about steel tension members? And then you didn't quite get, and we want to spend a little more time on. Good to go. So flexural members, right? This is bending, right? We've first talked about, what are the limit states? Well, there's flexural limit states. There's yielding, that's the formation of a plastic hinge. There's local buckling, that's the buckling of a flange, okay? Or lateral torsional buckling, that's another limit state that can happen, but that's a global buckling procedure. We'll get into those a little bit more. Shear, there's yielding of the web, buckling of the web, and then serviceability, we only looked at deflections. So like in terms of flexural limit states, what we looked at was the one that governs our LRFD stuff is this formation of a plastic hinge. That's where the steel yields over the whole height of the member, okay? And then it's calculated, right? I mean, it basically, the way you calculate this capacity is you just assume that the steel is yielded on the compression side, you assume the steel is yielded on the tension side, and then you could look at your C's and your T's and then sum the moments and stuff like that. Okay, the good news is AISC has all these things tabulated. We kind of went through and talked about the difference between the elastic section modulus versus the plastic section modulus, right? And how to calculate these capacities based off of this. But then really those Z values right here, Fy times Z, Z is tabulated in the code, okay? And even the AISC manual has actually gone through and organized these things based off of Z, right? Because that's a key property that we have in design. And so they've made a table that has these things sorted by Z's. And so I guess another thing, the elastic moment is Fy times F. The plastic moment is Fy times Z. The plastic section modulus versus the elastic section modulus. We did a little example with that. Okay, and then we talked about local flange buckling. Right, this is what local flange buckling looks like. You get, right, that flange was in compression and it buckled out. And notice that it's not buckling over the entire length of this member. It's just in one little place. That's why it's called local buckling. It's because it's just buckling in one small little spot. Okay, this is not going to be an issue for most wide flange sections, right? Because AISC is no dummy. They've gone and they've made this ratio, BF over 2TF, stocky enough so that it will hit the plastic moment capacity before you get buckling in one of these flanges, right? Very clever of them. It wouldn't make sense if they make these things slender versus compact. If they make those slender, then they're going to buckle and it reduces your capacity of your member. But if you make them stiff enough, stiff enough really, or just not slender, you make them stocky enough, you don't run into problems with local buckling, okay? And so for most sections, we didn't worry about that, okay? I think it's important to know what local flange buckling is, but then just know we don't have to deal with it. If you were dealing with like a built-up section where you make one of these yourself, where you just say, I'm going to take this plate and weld it to this plate and weld it to this plate, then you have to start worrying about this, okay? Or if you have like one of the 5 sections, you have to worry about it. For most part, though, there isn't an issue. Okay, and then we went on, we kind of talked about lateral torsional buckling. We'll come back to that. We introduced what it was. It's this idea that you get compression up at the top under normal bending, or, and it'll be on the bottom under negative bending, right? But on whatever the compression flange is, if you don't support it, this thing wants to buckle out to the side, and it wants to flip on its side. And if you look back in the YouTube, I've got a little video of Tim White. I got me here in the background too, the young guy right there. Right? No beard. We did some testing on this, and this thing, if you watch the video, you can see this thing go through some lateral torsional buckling. Okay, and then in this case, you got the compression flange up top; it's not supported, and so it buckles out. That complicates the design for sure. Okay, shear limit states. We'll go back to lateral torsional buckling in a minute, but the shear limit states either it yields across this web right here, or you get web buckling. It's the same mechanism that caused issues in tension in reinforced concrete, right? Tension in reinforced concrete ran into problems with, in this little example here, these tension forces is what we ran into problems with concrete, and we get a crack that would go like this. On steel, the web, we run into problems with these compression forces because this thing wants to buckle. And it would buckle kind of like in this direction here. And you kind of see this is an example of where they tested a member and got web buckling. Right, but similar to local flange buckling, AISC is no dummy. They made these the H over TW to be stocky enough that it's going to hit the plastic moment capacity before you get reduced capacity due to buckling. Okay, and so they really thought this through. Okay, we talked about stiffeners. Okay, and when shear would control or not control. And then we got into deflections. How do you calculate deflections? Well, usually there's some sort of limit. It's going to be some fraction of our span length, right? Live load, like L over this, most standard are your live load deflections have to be less than L over 360, or your total loads have to be less than L over 240. Where do these delta live loads come from? Well, they could come from solving this 4th order differential equation, or you look it up, right? These tables, if you go on into structural engineering, these tables are super helpful. Right, they have the shear and moment diagrams for all these cases. It's turned shear and moment diagrams and deflections into matching game. Right, you look at your loading conditions. You look at this. It tells you what your shears and your moments are. And it tells you what your deflections are. Okay, and then when you calculate your deflections, the other thing that you're looking up in this table, the other thing to be careful of is the units that you're using in these equations. Right, and then also you use service loads. Right? Nobody's going to die if you if your deflection calculations are not accurate. Okay, and so because of that, you don't use the 1.2 and the 1.6. You go straight up your service loads, what you actually think your loads are going to be. Okay, and that's kind of covered in there in this little section here. Okay, but then for lateral torsional buckling, okay. Oh, so how do you go about designing these things? Just really quick, right? Use the Z tables. The Z tables, right, have these things organized by the Z, right? You can either calculate this if the yield strength is different. You have to calculate what your required Z is, or you just look up PMP in the manual and just make sure that your PMP is greater than your MU. And then to do shear design, super easy. In the Z tables, you look over to the right and tells you what phi V is. Okay, phi VN. It tells you straight up for all the members. So that just checking that capacity is pretty easy, and then check your deflections. For that's a standard design, right? We did an example of a standard design. Right? You had homework with that. You guys should have that one down pretty good. The thing that gets a little complicated is if you have lateral torsional buckling, if you don't have supports along the length, then things get a little bit more complicated, but also not too unruly, okay? So lateral torsional buckling, again, is this top flange wants to buckle out, or if it's a negative bending, it's the bottom flange that wants to buckle out. Okay, and depending on what what governs that is what this unsupported length is. Okay, if this unsupported length is less than LP, which is something that's tabulated, then it's the plastic moment that controls. If that unsupported length is greater than LP and less than LR, it's inelastic lateral torsional buckling controls. It means you're kind of in this region. If your LB is greater than LR, then you're in this region. It's elastic lateral torsional buckling. And the code has equations for each one of these things. Okay? This one we already know. These ones are getting pretty complicated. But to do a design for this gets super complicated. Because if you look at the equations for this and this, there's no like simple variable to solve for to do design. So they have a method for doing that. Which we're going to get to. I mean, they basically have just plotted this curve for all the different members in one giant table. One giant table that spans 50 pages or something like that, okay? The other thing, though, to be careful of, the other thing that governs how susceptible something is going to be to lateral torsional buckling is all these properties, right? Material properties and geometric properties of the section. These would go into what LP and LR are, okay? The other thing that controls it is what are your end conditions, right? This end condition, right? I have 0 moment at the end, 0 moment at the end. So only, the middle part is in compression. In this case, this whole thing is going to be in compression. Whereas in this loading case over here, only this part is going to be in compression. And so this case is less severe than this case, right? So then this one will have you get rewarded with a CB value. So this is going to have a CB value that's going to be bigger than this CB value, okay? And so we have to account for this effect as well. How much is the compression flange in compression? Like what percentage of the length is in compression, as well as how extreme is that compression? In this case, it's not that extreme because you have zeros at the ends and zeros at the ends. This case right here, really extreme, right? Because you have the worst case compression stress along the entire length of the member, right? And so this is the worst case scenario you can have is 2 moments on either end, okay? And then you'll get a worst case shear moment across the whole thing. In that case, CB is equal to 1.0, okay? That is the worst case scenario, is make it CB equal to 1.0. How do you calculate what CB is? Well, there's this whole equation right here, and you think you did this in an example. We did it here. You did it in your homework, so you should know how to calculate what that CB value is. Okay. So CB's got to be in there someplace, right? It's in those capacity equations. If you look in the code, the design aids, we got Z tables, we got I tables. So if for some reason your deflections control, you can use I tables. Those things are just they've gone through all the members and they've organized them in order of their I's. And they've done that because just in case deflections control, they've got them ordered by their Z's as well. There's these max uniform load tables. I don't use those. Those are kind of weird. Okay. And then capacity curves are the other thing. That's what we did use. So again, what they've done is for every single member, every wide flange in their arsenal, AISC's arsenal, they've gone through and put all of them in one big giant table. And that's what that table 3-10 is. But what you're looking at each one of those pages are little subsets of this, right? Each page is like some component of this, okay? And then you just look at each page, and really, if you pieced them all together, you get the big picture was just looking at this. The way you use this is you plot your demand, MU and your MU and LB, you read up and to the right until you hit the first solid line. That gives you the most economical member, okay? Yeah, and so we got to use those tables. Those tables are specifically for when CB is equal to 1, worst case scenarios. It will always be conservative to assume CB is equal to 1, okay? But if you're not always trying to be conservative as a structural engineer. You want to be the most efficient, right? You want the most efficient section. No, your clients won't be too happy if all of their members end up costing twice as much because you were just being overly conservative, right? They don't want to overspend on their building. And so if you have to sharpen your pencil and calculate CB, you can use these tables, but it involves adjusting your moment demand. You take your moment demand, you divide by CB, and then you use that new moment demand in your table, and then you read up and to the right, and it does it. But in order to do that, you got to be a little careful about what's happening with the plastic moment. And I kind of laid out a process for how to handle that, okay, on how to handle that and just make sure that it's okay. And so that's lateral torsional buckling. Okay, we went through and did an example associated with that as well, right? And then we did it once calculating CB and once not calculating CB, but you get the same. You don't have to do it both ways. I just did it in this particular example to demonstrate. Okay. You guys have any questions about flexural stuff? Right, we haven't covered a lot in the last few weeks. I think maybe we have, but I think it's pretty straightforward. This is hopefully I like its steel design a little bit better. I think it's a little easier to grasp, to be honest. It pains me to say that. It pains me to say that. I concrete is where I make my living, so I feel like I think I do a pretty good job of selling it. And then columns. The last thing is the steel columns. Oh.
Hello?
Yeah, what do you got?
Sorry. Didn't know if my mic was working. I had a question from that homework. I'm trying to see how to word it and get back in that whole in that material. Something about it says the required I for the deflection limits always lead to the same beam that you got from the other limits.
It shouldn't. I think it might have in that example, but it doesn't have to, Amanda. I think when we did an example, usually it required I. Is that what you said?
Yeah.
Yeah. When we did our example for that one, I don't think it did, right? I did one where I gave more stringent deflection calculations or deflection limits. Let's see here. This is without the lateral torsional buckling stuff. We did one without lateral torsional buckling where I said let's pretend I demonstrated the use of the I tables.
Mm-hmm.
Yeah, this guy. Right, so we designed this one to begin with, right? Just based off of the moment demand, and we came up with a W21 by 44. And then we checked the shear and we checked the deflections, and they were okay. But then I said, what if this happens? What if we have a more stringent deflection limit, like L over 720? So this happens sometimes. If the contractor has a certain floor that they don't want to feel like any movement whatsoever, if they've got equipment in there that's fatigue sensitive or that's vibration sensitive, they might come out and say, let's make these deflection limits super tight. And in that case, we went back and we solved for the required I, and we ended up with 1560 for that required I, and we used the I tables, and it came out with a W24 by 68. So when deflections didn't limit, a 21 by 44 was fine, but then when deflections did limit, we needed to make it deeper, down to 24 by 68. And so it doesn't always have to be that you get the same based off of that I. Did that answer your question, or?
Yeah, I think it had to do with like there's two different kind of deflection limits. If you know, if
Yeah, there's the live load and the dead load deflections. Is that maybe what it was? Is this?
oh, the live load deflection and the total load deflection.
Yep. Oh, I made a mistake.
Was it's live and total, right?
Yeah, it's total. Yeah, there's my notes have a mistake. I wasn't
Like
done with it yet. Oh, let me finish. There we go. There we go.
on the homework, the live load deflection came out to like the same beam as the total load deflection. So I just wondered if you had to do both of them.
Yep, I think that just happened to be that way. I think it would depend on the ratio between your total load and your live load, right? If you had if the live load was 90% of your total load, you get a different thing than if your live load might be 10% of your total load. So it depends on the ratio between your live load and your total load. I think maybe it just ended up being the same beam on that example.
Yeah, and that was that was my first time calculating those because we didn't do deflections in the example in class. So I just wondered. But
Yep. And so it's also, I should point out too, these deflection calculations, right, are kind of independent of like the lateral support calculations, right? When you have those lateral supports, like in like if they're spaced at, whatever they were, they had it at like the third points, like your homework had them where they were spaced at the third points or something like that. Those lateral supports will not affect your deflections at all. Right? They're just there. It doesn't affect your moment. It doesn't affect your supports. They're just there to prevent that top flange from buckling out. They don't resist any vertical loads. They're just there for the horizontal load that comes from it wanting to buckle out. So you'd use these same appropriate equations as if those lateral supports weren't there. I know that students in the past have kind of messed up that a little bit. It's worth noting. Any other questions on that? Okay, good. Okay, so columns, right? That's the last thing we covered in the last, maybe 2 lectures or so in the last week. Okay, you're going to find all those components here, Chapter E, Chapter C, column tab, Appendix 7, and the commentary. Okay, right, so then let me just open up those notes. Right. So this whole idea, what we did is we kind of started out the limit states again. You're going to have yielding, global buckling. Those two are the ones that we're going to worry about in this class, or that we worry about, because the local buckling is probably not going to be an issue because we have compact sections. We have the flanges and the webs thick enough so you don't have any buckling of local components. And so we're only going to deal with these 2 limit states in there. And then we kind of talked about where you find all this stuff. Again, you're going to have a capacity curve. You're going to have the capacity being yielding up here, and then after you hit a certain point, you start having buckling control, and the factor that's going to control that is this KL over R. That's our slenderness ratio for columns, right? So again, this is just another example where you see this capacity curve throughout. The buckling phenomenon in general, I wouldn't worry about this too much. Just it's kind of did you guys cover this in mechanics of materials? Did you talk about buckling in mechanics of materials? No, that was 2 semesters ago. Who knows what you covered? No, you don't remember it, but it's a cool topic, right? If you ever get a chance, in grad school we talk about this a little bit more, but buckling's kind of neat. This whole idea of applying this load, having this restoring force that this stiffness that kind of pulls it back into place. At some point, the moment from this load will overpower the restoring force and the thing will buckle. And you can mathematically show that it doesn't matter if you tap it from the side or not, it actually will collapse. That's the same idea that Euler did back in the day. He looked at, beam bending. It doesn't have one of these springs, but the beam doesn't want to bend sideways, so it has resistance to that. Bending of the beam wants it to pop back into place. And so you can, he went through and just, looked at what moment was coming from the axial load, what moment was coming from the bending. You set them equal to each other. That's where you're going to determine with buckling. You solve it and you get this load, and that the solution is a half sine wave, right? And instead of solving this for every, this is specifically for a certain load condition or end condition, which is a pin and a pin. If you had a fixed up at the top, you would get a different answer. If you had a fixed and a fixed, you would have a different answer. If you had a side sway, you would have a different answer, okay? And so instead of having a bunch of different answers, they just modify this value with this K value out front. And that's the same, it's the equivalent to the solution of solving this thing with different boundary conditions, okay? And so they've done this for us. They said, here are all the different boundary conditions that you can have, okay? And what you're looking for is where the half sine wave is, okay? You don't really need to do that, right? That's just to explain where it's coming from. It all comes from this. I don't know where my notes are there, but you can see the half sine wave in this case goes all the way down there, so that's twice the length. Half sine wave here, okay, is over there, and so then that's why these guys get K's of 2, right? But it's to account for these different load conditions and the effect that they are going to have on stability, okay? Using those K values, right? We went through and calculated this equation that AISC used. For some reason, they talk about buckling stress as opposed to buckling load. And so we kind of turned it in terms of that. And this equation shows up directly in the code. And so here's what the code looks like. We spent a little bit of time talking about that, right? And they kind of lump 2 failure mechanisms into one. They have yielding and inelastic buckling is kind of this region right here. And then from this region on, it's going to be elastic buckling that controls, and there's the equations for that. This is almost the same as this equation that you see over here. Okay, the only difference is this 0.877 that's out front. I like to see that as a concrete person. I like to see that they're using empiricism as well. It's not just the concrete people that are doing it. They do it too, right? And that's to account for initial crookedness, okay? But for the most part, we don't have to use these equations, okay? Because AISC is no dummy, and they've provided us with some load tables, okay? The things get a little bit complicated, right? Because of this whole weak axis versus strong axis buckling, right? The code, right? In this case, a lot of times you'll support a weak axis. This is an example of them supporting a weak axis, but not supporting the strong axis. So in the strong axis, it would buckle over this whole height. Over the weak axis, it could buckle over these heights right here, right? Which one is more likely? The weak axis buckling over a shorter distance, or strong axis buckling over a larger distance? You don't really know. You can't really tell, okay? And so that's why, that's kind of what this whole other stuff was about. How do you use these design aids? How do you use the design aids? Because they're based off of buckling about the weak axis. What you do is you come up with this KL equivalent by dividing by Rx over Ry, and then you can use those tables, okay? And then if you remember the video, if you watch the whole video, I struggled with explaining that a little bit, okay? But I got it down. I think I came back, I nailed it. I think I nailed the reason why you do that. The beginning of the code also tells you that. If you look right before those design tables, if you look right before it, it says in the code, it says specifically to do this, to divide by Rx over Ry, to use it for strong axis buckling. The other thing I should note too is that I have a PDF of the old code, and so the old code calls it KL. Your code, the teal code, the teal steel, it uses LC, I think is the variable that they use. It's the same thing. If you look at the beginning of the table, it says, oh, by the way, LC is KL. But for whatever reason, they've moved to using LC as opposed to KL. And then we did an example, and you did a homework problem similar to this as well. I should also point out, I wanted to point out this too, was, oh, I got it down here. Right, you did this homework problem. This is where I messed up in my solution. Right, for some reason, I ignored the fact that this is 17 feet here, and I just used 10 feet. So if you didn't look at the solution, it should be 17 feet. I've updated the solution that has the 17 feet in there, so it should be better. The other thing is when you calculate that KL over R, when you're trying to look at this, I saw this quite a few places. Like if you're trying to see where at on this curve, you got to be careful of units. Your KL is probably going to be in feet. This stuff is going to be in inches. Okay, and so you got to put your KL over R needs to be in inches. Okay, you have to take your KL, multiply it by 12. Your Rx or Ry, depending on which axis is controlling, is going to be in inches. This thing goes in KSI. This guy can go in KSI, and then everything's fine. So if you got they should be close to each other, those limits. I think some people got like 6 or something. That's because you left it in feet. It should be around 100 is what it should be for those limits. But just be careful of your units for using that. The other thing I wanted to note is we only used, right, this is the table that you use for design. We only use the ones for wide flanges. They have wide flanges, like a W12s. They also have W14s. They also have, I don't have it on here. What do I got? They also have it for a bunch of different members as well. Let me see here. All right, so table 4.1, it gives us for these are for W14s, and then they give us W12s. I think on my notes I just said that they had W12s and W14s, but they also have, I think if we keep going, they also have W8s, I think. Let's see if I can get to it. Oh yeah, W10s. They do W8s as well. They also do HSS sections. Okay, they have HSS sections in here. They have square HSS sections, right? Well, somewhere in here they have square HSS sections and stuff like that. So I just wanted to point that out. I think in my notes or when I was lecturing, I was like, oh, they got these things for W14s and W12s. They have them for W14s, W12s, W10s, W8s, HSS sections, square HSS sections, right? So they do have it for a variety of sections as well. But you read them and use them all the same, okay? You look up what your KL is or your LC is. This is your weak axis buckling on your left over here. You're just looking up what your VPN is for each of these different members as you go across. Right? I just wanted to point that out too. It's something I missed. I missed before, was pointing out that those existed. Major versus minor axis. You got to be careful of that. Design aids, where to find them, how to use the column tab. Yep. Cool beats. You guys have any questions? Concerns? Last word.
Mike.
Yeah, Paul.
Mike, just on the lab report resubmittal, just do that through D2L.
Yep. I think that I think that it was set up. Wait, hold on. Yeah, so it's set up that I think you could do a resubmittal right through the same assignment portal or whatever, right? I think that'd be the easiest. That being said, if somebody else wants to turn it in, I'll find it, right? I think it'd probably be easiest, though, if the people that turned it in originally turned it in again, just under the same feedback that I gave back. And were we all able to find that feedback I gave back? Right? It's just like I just took a PDF. I just took a picture of what the engineering or English majors gave me, and then I handed them to you guys. And so I think there's a couple people that couldn't find them necessarily, but hopefully you were able to find them. I don't think they're too extensive of edits that you have to do. And so, I mean, take a look too at what I'm doing with the grades. Hopefully you guys are okay with it. I think it benefits you pretty significantly, right? If you participated in the lab, I think that was quite a big portion of it. I think having, I took the missing lab reports, I spread it out amongst a bunch of different categories and stuff like that, and gave the lab participation some factor. And then you only have to write one lab report as opposed to 3 of them. So that's also should be a positive. So everybody hanging in there and enjoying this, hating this, losing your minds. Now you hating it. What do you guys say? Are you all coming back next fall? Anybody not coming? You guys are invested now, right? Like, right? I think the university is really worried about enrollment in the fall because it's going to be weird. It's going to be weird. I don't know if you're paying attention to it. It's going to be like, I think like I'm teaching dynamics in the fall. I think that's going to be all online. I don't think you can meet 150 students in a way that will promote social distancing. So I think that's going to be online. They might stagger classes where you come some days and not other days, and then they're online the other days. It's going to be weird. I think mainly where they're going to have issues is freshmen, right? Like if you were a freshman, would you start in the middle of this or would you wait 6 months? I think I might wait 6 months, right? I think I would definitely do that, right? It's weird. But then again, Bozeman's a pretty safe place to be right now until all those people come here, right? Are you guys all in Bozeman right now? You got any? Are you in scary places, like anybody in New York City or anything, like right in the middle of it all? No, that's good. I'm assuming it's pretty calm where you guys are at least for now. No, where are you at, Hannah?
I'm in Seattle.
Oh yeah, it's not calm there at all.
No, my sister actually works at the hospital where it first started, so
Does she work at
that's kind of
Evergreen?
crazy. Yep.
Oh, my wife works at Evergreen.
Really?
Yeah, she does telenursing there.
Okay.
She does and she's been super busy because they don't want people going to the emergency room, and so they call and they talk to her beforehand. She screens all that stuff. So interesting. Yeah. So is she living at home then?
Yeah, she is.
What the hell, Hannah? You should get her in there.
Yeah, I know. But I'm going to come back to Bozeman, so I might be one of the ones bringing her.
I know. Hopefully people do the whole that's the thing is once everybody gets here and everybody if they do what they're supposed to do and self quarantine and stuff, then we're gonna be fine, right? Because then it won't come back into the community and we'll just be fine. Gallatin County has 0 active cases right now. Awesome, right? But until people start going out and then doing things, then coming back and not quarantining, and then it just goes again. So where you at, Elizabeth? You said you're somewhere, right?
I'm in Florence, Oregon, so it's on the Oregon coast.
Okay, it's not too bad there
Pretty
now,
calm.
right? Or
Yeah, it's there's only 8,000 people that live here, so it's pretty calm, and they closed all the parks and beaches, so nobody comes here.
yeah, it's also boring as hell, right? Right. Just we've all lost the will to live, but we're safe, I guess. So.
A little bit.
Yeah. Cool beans. Well, that's all I had for you guys. I mean, I enjoyed teaching you what I could. I mean, the first half was great, right? At least I enjoyed the first half of it. But I'll tell you, we're sitting in my, you can see that I set up a home office in my bedroom. I commute from right there to right here, and it's pretty boring. I'll tell you that. When I sit here and I lecture usually I do it in the evenings. I'm lecturing in the evenings just by myself in this room, making jokes to myself. It's pretty boring. I miss you guys, is what I'm trying to say. Hopefully you do come back. No. Cool beans. You guys have any other questions, concerns, anything? Good to go.
Thanks for everything, Mike. Appreciate it.
Bet, guys. I've enjoyed it. Like I said, I don't think I'm not making this thing any harder than I have just the finals in the past. So you should be able to do it just fine. Okay. And then if you have any questions that come up during the process or whatever, reach out and I'll be available via email or WebEx or whatever you want to help out. So cool beans. Keep it tight. I like tight homework solutions. Nice and to follow. So cool beans. Take it easy, guys.
See ya.
Yep.
Thank you.
Yeah.
Yeah.